As you're aware, I didn't get around to recording a different lecture. I said too much. What? I don't know. I don't know what's happening. This side's fine.
My monitor wants to hit the snooze button and go back to sleep.
Yeah. I don't know what's happening. Yeah, I think you're just gonna have to. Oh, okay. So I didn't get around to it. I had too much to catch up that I was doing because I missed most of Friday and Monday. But I kind of went through the notes. I think we got a good plan. I'm going to kind of rush through this little section, start the next section. And what I'm going to do is I'm going to record a couple of example problems, and then I'll post that on YouTube so that you can kind of have enough information to do the polar coordinate problems that are out of your homework. So I'll try to post it this afternoon. You can watch it tonight. You can watch it tomorrow. It's just it'll just be me doing examples related to this that'll help you do the homework. There's also recitation this evening, and then your homework's due on Friday. And then all the material that we're going to get through today and the example problems, that's what's going to be on your first exam. So what we finish this week will be on your first exam, which is next Friday. Okay? And so the way just to give you a little foreshadowing, the way that I do my exams, I just give you 2 problems, okay? And then you just work out the 2 problems while we're sitting here. There's no short answer, true, false, none of that stuff. It's just, can you do these problems? Me versus you. You get 1 sheet of notes, okay? You get 1 sheet of notes. You can write down any equation and stuff like that, or equations that you want to include in there, and then we're going to go from there. Yes?
Is it front and back for the sheet?
Just 1 page, just 1 8.5, so just front, not back, right? The final you'll get to, and then just keep a hold of these things because then you can use them all in the final, basically is what we're gonna do. So, and then it's 2 problems. The 2 problems are gonna be, one is gonna be 2D particle kinematics. So that's the problems where we're just looking at geometry of motion, everything we've been doing up until we started talking about forces. And then 1 FMA problem that's kind of off of the homework you're doing this week, okay? And it'll just be 1 of each of those problems, and then we'll do them. I think I'm going to split the class up because I think the same thing that Kirsten's doing. We're going to have another room. The half of you is going to go to the other room, and then half of you are going to stay here, and we're going to do that. We're going to proctor it the old-fashioned way, and then I'm going to upload it to Gradescope and grade and stuff. Any questions about that exam? That's next Friday, not this Friday, next Friday, okay? And it'll cover everything that we make it through by this Friday. Okay, so what we just did, the topic we were talking about, actually last Wednesday, a week ago, right, was the kinetics. How do the forces relate to motion, right? And it's just F equals ma. This is the first way we're going to solve it. We're also going to do work energy and then impulse momentum. But this is, and then we're going to go through, we're also going to go through 3 coordinate systems as well. The first coordinate system we did was the Cartesian coordinate system. It just looks like this. Sum of the forces in the x, the y, and the z, and then they're equal to the respective mass times accelerations in each one of those directions. So you just treat them as 3 different problems, essentially, right? We talked about free body diagrams are going to be huge. We talked about writing the procedure used to come up with these free body diagrams, and then our solution procedure. We're going to stick to this every time. Even though you think you might know how to do the problem without doing it this way, do it this way anyway, because this is going to be worth points, right? You're going to do a free body diagram. You're going to write down the equations of motion. The equations of motion are these guys right here. And then you're going to do the kinematics as required. Sometimes they're not super required, or they're not as important to solving the problem. And then you're going to solve it, okay? And we did a couple of examples. We did this spring, right? And drew our free body diagram, wrote down our equations of motion, and then did our kinematics, and then we solved and got our answer, okay? We're going to stick to that process every time. Did the same thing here for this block that was sliding down the inclined plane with this cable attached to it like this, and we drew our free body diagram, wrote down our equations of motion, and then did a kinematics. Our kinematics in this case was just identifying what our accelerations were and plugging them in, but it was pretty straightforward, and then we solved for our unknowns. Okay, so that was the Cartesian coordinate system. The next coordinate system that we're going to do is the normal tangent coordinate system. All right, some pretty interesting stuff starts happening. If you remember, normal tangent coordinate system, our coordinates look like this. You had one coordinate that was pointed tangential to the path, and then another coordinate that's pointing back to the instantaneous center of curvature. So this would be our ET hat, and this would be our EN hat. Okay, to kind of review what our accelerations were in this coordinate system, right? I guess one of the key takeaways was our velocity is always in the ET direction. That was this kind of review of the kinematics in this coordinate system. Velocity is always in the tangential direction. Just it has to be if it's on that path, it has to be in that direction. And then that EN is changing as you go along. Okay, the EN, if it curves the other direction, EN will flip directions, and it's not constant. Okay, for accelerations, we determined that there's going to be some acceleration along the path, right, in the ET direction, and that's just going to be our change in speed in the ET direction. And then there's also going to be an acceleration component associated with the change of direction, which is always going to be in the EN direction. That's the change in direction. It's always going to be in the EN direction, as just by definition. And our accelerations there are going to be one of these two. Right? It's either going to be, if we have the velocity, it's going to be v squared over the radius, or if you have omega, it's going to be the radius times omega squared. And so what that looks like in our, that's just the acceleration equations, and we just substitute them into that Newton's second law. Some of the forces in the tangential direction is equal to mass times acceleration in the tangential direction, which is just mass times the change in speed in that direction. Right? So when we write down our equations of motion, right, we're going to know how that acceleration in the tangential direction is related to v, using that equation right there. Right? And then in the normal direction, when we write down our equations of motion, right, and we get to this point right here where mass is equal to, or the forces are equal to mass times acceleration in the n direction, we're going to use either one of these. We're either going to use mass times v squared over rho, or we're going to do mass times rho omega squared. So we just, when we write down our equations of motion, we write down one of those, depending on, again, if we have the velocity or if we have omega. And that's it, okay? So we're going to follow that same procedure, free body diagram, write down our equations of motion. Here are our new equations of motion, right? And then we're going to do kinematics as required, and then we're going to solve. Right? And they're all very straightforward. I really like this section of the class because it's very dialed. It's just like, here, follow this process. It leads you there every time. Okay? Even if you don't understand what's happening, just follow the process, and it just leads you there. Okay? As long as you do all the steps correctly. Okay, let's do some examples. I thought this was pretty funny. So this is a car I drew. I thought that was pretty good. Right? I'm not a good car drawer, right? But I drew that car. And then I saw this meme a few years ago. Right? And it says in kindergarten, but actually this is how I still draw cars. Although this time I think I'm pretty good. That was a pretty good car. Okay, so this car is traveling right up this curve, right? And then right at the cusp of it, it's going to either jump, right? We're trying to find the velocity, if you read the statement up there, either the maximum velocity so that it stays on the ground, or the minimum velocity for it to launch into the air, right? And I think it's more exciting to think about the minimum velocity before it jumps into the air. Right? A little more exciting. It's hip and cool to jump your car, but it's not to drive just slow enough so you don't jump into the air. Although I do a lot of biking and snowboarding, but one of my major goals is to never leave the ground. And so I'm actually as I get older, I've had 3 ACL reconstructions. And so my goal is to always just keep my body on the ground. And so I'm usually finding the maximum velocity that I can go in order to stay on the ground and not actually catch air, because I don't ever want to catch air. It's terrifying. I'm just lost in the air. Okay, so let's do this. So let's do this example. So you're like, oh God, where do I start, right? What do I do? How do I do this, right? Draw a free body diagram every time. Just stop panicking. Don't worry about what's happening, physics. Obviously you have to care about what's physically happening and stuff, but don't rely on your intuition. Just stick it to this plan. Draw a free body diagram. So one free FBD. BD. Right? These particles can be drawn as points, so let's do a point. So that's that car up at the top there. Force is acting on it, right? What are some forces acting on this car? Where's the guy? There's a guy over here that's supposed to call out gravity. Wasn't he over this direction? Is he not here today? There we go. That's you. That's you, man. You're letting us down. Okay, good. Gravity. That's the easy one, right? Almost always there. Mass times gravity go in that direction. What else do we got? What? Normal force. Kind of. We'll talk about that in a minute. Right? It's just of this car. This is this car right here, right? That's it, right? We have mass times gravity acting down. We have normal force acting up, right? Right. Our free body diagram. I mean, that's our replacing our forces. Our free body diagram is not complete yet because we need to put our coordinates on here. Okay, that's part of drawing a free body diagram. My coordinate system in this particular case is going to be this guy here is going to be my ET direction. And this guy right here is EN. Right? Because this guy's traveling on this path, right? It's traveling like that. And so that its tangential direction is or its velocity is always in the tangential direction, right? And then this is pointing back at the instantaneous center of curvature, so it's pointing back down to the middle. So that's it, ET and EN. Right? Again, that's it, right? I mean, there's no dimensions really that we need to put on here. That's just kind of everything that a free body diagram needs. Okay, perfect. So then we come over here. Second step is to write down our equations of motion. Right? The reason there's no, by the way, I have no forces in that ET direction is because it's traveling at a constant speed. Right? If it was not traveling at a constant speed, it would have to be accelerating along the path, which means there would have to be a force that direction, which would be like, you know, the guy stepping on the gas, which would be causing the wheels to torque, which would be giving him a thrust forward, right? So there would be a force in that ET direction. But in this case, it was a constant speed. There is no forces in that direction. There is no acceleration in that direction, right? So you could write a force here, right? Call it Ft. And then since it's not accelerating that direction, that would just go to zero if you want to. I just assumed that's it. Okay, so my equations of motion. We got the t direction. We just talked about that. Let's just put it down on the paper here. T direction. Sum of the forces in the t direction is equal to mass times acceleration in the t direction. Again, this is zero. It's not accelerating the tangential direction per the problem statement. And so this force, the whole thing is equal to zero. So some of the forces in the t direction, there's nothing going on there. Right? Okay, and so now where the exciting stuff is happening is in the EN direction. Okay, so we have some of the forces in the N direction. We have, and then just be careful of your signs when you go in here. We got mg, right? That mg is the En direction, but it's acting in the direction of En. We've drawn En like that, so that mg is going to be in the En direction, and then our normal force is going to be in the negative En direction because it's acting opposite the direction of this. So the only forces we have here are going to be minus N plus mg. Right? Important to get those signs correct. You won't get the right answers if you mess those up. Mass times acceleration in the N direction, which is just mv squared over rho. Okay? That's what I mean before. It's just, and when you get to this point right here, instead of EAN, you substitute in what AN is in that coordinate system, which is mv squared over rho. I could do m rho omega squared. But they're after the speed, right? They're after the velocity, and so I could solve for v. I could solve for omega and turn it into v if I wanted to. It's interchangeable. Okay. We have a little bit of a problem here, though, right? Is I have this equation told us nothing. The force is in that direction. This equation is the only other one we got, right? And I got two unknowns in here. I don't know what the velocity is, and I don't know what the normal force is. Okay. But then we do know something about the normal force. What's the normal force in this situation? 0, right? We're trying to find it right at the cusp of the thing taking off, right? So if it's right at the cusp of taking off, the ground is not going to be pushing on it anymore, right? Make sense, right? It's right at the cusp, but that normal force is going to be equal to 0. This shows up in one of your homework problems, that concept, so just keep that one in mind, right? That normal force will be 0. And so in this case, this guy is just going to be 0. Right? And so there's one equation, one unknown. You just plug in the variables, and you get it. Let's see these guys. Keep going with this. This mass and this mass cancel each other out. Go ahead and solve this. Usually I just plug it in my calculator, but I'll put in the terms here at least. G is equal to v squared all over rho. G, be careful of the G's you're using. This thing's in English units, so it's going to be 32.2 is equal to v squared all over 200. Everything's going in feet and pounds, right? In order for this our units to work out here, everything goes in feet and pounds. And then if you solve for this, this guy becomes, we solve for the v. So v ends up being equal to 80.2 feet per second. They're not bad problems, right? They seem maybe scary a little bit at first, but then just stick to this, and it literally leads you to the solution every time. Any question about that one? We caught up? We got other stuff? All right, we'll go to the next one. Okay. I got this. Let's see here. I got a setup to this one. So this is gonna be a big rope swing. Okay. These guys are up here, and they're gonna jump off, and it's gonna swing around. The capacity of this rope, that tension that rope can carry, is 2,999 pounds. Is everything gonna be okay? Here's my build up to that. This is a real life story. Prepare your ears. It always gets very loud, right? I can't control the volume, so.
There's only one way to go, and that's right over the edge.
So should I put this T-minus 10?
The plan, drive to a predetermined spot on the bridge, attach a 200-foot-long cable to a parked limousine. The 5-member stunt squad runs the swing end of the cable to the side of the bridge. Each jumper would attach themselves to the end of the cable and then jump, swinging out like...
Real quick, did you guys see that GoPro on that guy's head? Did you see that? It's a full-size camera on his head.
a pendulum.
There we go back here.
Then release the cable and escape before police, Coast Guard, and fire department authorities can capture and arrest them all. The stunt requires precise execution. The camera crew in the helicopter is ready. The camera crew below the bridge is set.
Right there, see it?
The 5 daredevils jump.
Okay. This is an exciting one, right? Is everything gonna be okay? Okay, so let's do some quick counts to see. We're gonna come back to it. We gotta do our counts first. Okay? Is everything gonna be okay? Okay. So first step. What's the first step? Free body diagram. Okay. So let's go through it. F, B, D. Right? These things could just be points because it's that group of people are particles. Right? I'm going to draw it in, right? Technically, this is moving, right? as they jump off, they're moving, and so the angles in here kind of change as we go along. But I'm just going to draw the free body diagram as if it's in the point right here. Okay. So, what kind of forces are acting on here? It was close, man. I was close. It was close. You were talking. And you almost missed it. Mass times, but good over here. Try to beat the guy that's supposed to do it. Got mass times gravity acting down. I'm gonna move my label over to this side because I'm gonna break it down. What else? Tension. Okay. Tension in that rope. Okay. Any other forces acting on it? Right, technically, there's going to be drag, right? But if we ignore drag, passing through the air, that's it for the forces. Not it for the free body diagram yet, right? We need to put in dimensions. We have to put in our coordinate system, right? I do it all on here. Otherwise you get all. Yeah, it's just they're all really important, so you have to include them all. All right, so where are my coordinates at? You got EN pointed back here, right? Because it's traveling. EN hat, right? So this is, picture this thing. It's traveling along this curve right here. So EN is pointed back at the instantaneous center of curvature. The other one's going to be tangent to the path, which is going to be like that, which is not in the direction of gravity. It's this. Your EN is going to be here. Okay. Then we have to label. So those are our coordinates. We have to label, or we should label, angles and stuff, right? Dimensions. So this is going to be theta. That's just how I'm going to define it. I'm going to define that as being theta as it goes around, because it's going to be changing. That angle is going to be changing. So that's a variable. Yeah. I wasn't done yet. Thank you. I was just going to say, what's wrong with my coordinate system? Let me finish. All right. So is my theta right there. I'm going to define that as theta. It's going to be changing, right? And then I at least starting out, I like to put my breakdown of my force here, because this mg isn't in, just the en direction or the et direction. It's got components to it, right? And so I like to put those components. I can't even see that yellow. I'm not going to use yellow. You can have this component. You have this component. That's just the breakdown of that mass times gravity. And again, this is theta. This is not theta. That is theta. Theta, not theta, theta. And so this one, we'll label that curve while we're at it, or that theta. All right? So that should be my complete free body diagram. Right? Next step is to write our equations of motion. EOM. Some of the forces in the n direction are equal to T. And we could see them here. It's this and this. Those two guys. Those are the forces in that EN direction. Right, that's why I like to draw. That's why I like to break this thing down, is so that it's really clear. It's that guy and it's that guy. Right? So it's got T, it's in the positive direction because it's acting in the EN direction. T minus mg sine theta is equal to m acceleration in the normal direction and then we just substitute in mv squared over rho, or m rho omega squared. Either one of those. Okay? That's the forces in the n direction. some of the forces in the t direction. Right? Again, you can see him over here. There's just this guy. There's no other forces acting in that direction. So that's just going to be mg cosine theta. Right? It's in the positive ET direction, right? It's going that direction. That's positive, so it goes in as positive. Mg cosine theta is equal to MAT is equal to MR alpha. And if you look up, because this thing is going to be traveling in a circle, if you look back at our kinematics of something traveling in a circle, that acceleration in the tangential direction is just going to be r times alpha, right? That's the tangential acceleration. Okay? And so right now, right, we've written down our equations of motion. Right now we can't, what we're after is this t, right? We're going to compare that t to the 1,999, right? Is that what it was? Oh, sorry, 2,999. If that t is bigger than 2,999, then it's going to fail. If it's less than it, it's going to be okay. So we're after that right there. I can't quite get there because I don't know what this omega squared is, or I don't know the velocity, okay? But I do have an equation for the acceleration, right? This guy over here, I can solve for the acceleration. I'm going to solve for that acceleration, do a little bit of kinematics. I'm going to determine what omega is. I'm going to take that omega, put it back up into here, and solve for that t. That's what we're going to do. Okay, so, right, so we kind of hit a stopping point. We're like, oh, God, what do we do? Well, now we do our kinematics. We have to do kinematics, and that'll help us with the rest of it, okay? So before we get there, let's get our alpha equation for alpha here. That's the acceleration equation. Once I get an acceleration equation, I can integrate and stuff to get to what my velocity is, right? And so let's do that. So let's solve for the acceleration. A couple things here. I think just for solving that guy, you can divide by the mass and all those things. Those all go away. And so you could solve for alpha, and it ends up being g times cosine theta divided by the radius of curvature. And this is an accel, a function of position. Of position. Run out of the room. Okay. And when we did these, if you remember, there was a method for doing this. You look back in your notes. How do I solve equations or acceleration equations when they're functions of position? I have to use the chain rule. d omega, d theta, dt. And that's just omega. Okay. And so then you put the d thetas together. So we have alpha d theta is equal to omega d omega. It's kind of a pain in the butt because we are doing a little bit of integrals. Most of these problems don't involve this, just this particular problem. We have to dive a little bit deeper into our kinematics and actually do some integrals, right? So I'm going to substitute in what alpha is here. Alpha is g times cosine theta divided by r. I'm going to take the derivative of that with respect to theta. I'm going to integrate. And that's going on the other side. We integrate 2. And this is going to be omega d omega. We can put in our bounds here. So we're trying to find the maximum speed. The worst case scenario is going to be when these guys are going the fastest. The faster they're going, that's when when that tension force is going to be the most, right? So where are they going to be going the fastest? Down at the bottom, right? Down at the bottom. So then what's theta going to be when it's down at the bottom? It's going to be pi over 2. It's going to be at 90 degrees, right? Starts out up here, and then they're going to be down there. So our bounds on this thing are going to go to 0 to pi over 2. Right? And then what we're after is this bound right here, WF. Right? So what would I do at this point right here? I put it in my calculator. Yeah.
I just have a question about like knowing when it's like the strongest or whatever. I mean,
Yeah.
Intuitively, it makes sense.
Yeah.
Being at the bottom, but like how would you prove that? Or
Yep.
you know,
Uh-huh. Yeah, I mean, you would solve this thing as a function of theta, and then you could actually you would see instead of putting in this bound right there as pi over 2, I would just put in theta basically, and I would get a function of my velocity as a function of theta, and then you would see that it would peak out at pi over 2, if that makes sense.
probably just cosine there.
Exactly, right? And so based on that, you would see, oh, well, cosine is going to be 1 when it's pi over 2 or whatever it is, and then you would see that that's the case. That's a great point. Yep, because that would, I don't exactly know what this is because I put it in my calculator and I said solve for this, right? And then it did it, but consider using your calculator to do this stuff. You can. You're allowed to do it. Learn how to do it, okay? And so what my calculator said, right? And in fact, I put it in just like this. I didn't even like you could put this in your calculator and get an answer, and then this in your calculator and get an answer, and then use the solve command to solve for this unknown right here. Or you could put the integral within the solve, and then you could solve it within the solve. That's how I did it. You could skip that step. That's an advanced maneuver. So omega ends up being equal to 0.567 radians per second. One thing I don't like about this problem is that, right, we do it this way, and well, I guess what's nice is you get to see what a kind of a pain in the ass to get there. Our next thing after we do F equals MA, we have one coordinate system to do, and then we move into the next thing. The next thing is work energy. This problem screams work energy, right? It's way easier to solve it. Work energy, if you remember, right, you have potential energy, and you have kinetic energy, and you have all these other energies floating around. In this case, they have a potential energy of mgh, right? Starting out up here, have mgh, and down here at the bottom, they'll have 0 potential energy. So all that energy goes into kinetic energy, which is just 1/2 mv squared. And so if you do it that way, just 1/2 mv squared is equal to mgh, and you solve for that velocity, and it gives you this exact same answer, and you don't have to do this weird integral chain rule stuff, okay? So we're headed that way, right? And so if you were thinking to yourself, why don't you just do energy? We're gonna go there, but in this case, we're not quite there. Okay. So we take that omega right there, and you take it and you put it back up, right? That's that same omega, this guy right here. Right? Now that I know it's the velocity down at the bottom, I plug that in. So we get T is equal to, T, I'll just rewrite it down here. T minus mg sine theta equal to mr omega squared. So you can solve for T, right? T is equal to mr omega squared plus mg sine theta. And so I'll just kind of finish it off so you can see me putting all the variables in. The mass, you gotta be careful, right? There's 1,000 pounds of people. That pounds is not a mass, that pounds is a force, right? And so you have to divide by gravity to get it into mass. So our m there is going to be 1,000 divided by 32.2 to get that sucker into slugs. Okay, the radius is 200. Everything's going in feet and pounds and slugs. This omega is 0.567. That's going to be squared. Plus mg is 1,000, that's all of mg, times sine of pi over 2. There's just going to be 1. Okay. And so if you plug that into your calculator, your T ends up being equal to 3,000 lbs. Is that bad? Right? That's bad. That's bad, right? 3,000 pounds. The capacity of that rope is 2,999, right? So what's going to happen? What's that? It's gonna snap, and then where are they going? Where are they going? Where are they going? It's breaking right at the bottom, right? We hit that 2,999, 3,000 when it's at the bottom. So where are they going? This way, right? They're coming out, and then they're gonna be whipped. They're gonna be whipped that way. They're gonna go off on that tangent, right? This restoring force that's saying you need to change direction, that's going away, and so they shoot off at a tangent, right? But then gravity takes over, so then they go like that, right? Nobody dies. Just have to preface it that. At least, yeah, nobody dies.
Slow motion replay of the failed stunt shows that the Daredevils did not have enough pressure on the cable when they jumped.
That's not true, right? You'll see that you'll see that a lot, right? When a layperson tries to explain the physics, and then just like, oh, and what they're saying is that there was slack in that rope, and then when they jumped, when there was like a taut, like ripping, like an impact force when they hit it. But you could see that that's way gone by the time it breaks, right? That would have broken, like, if that was the case, it would have broken like immediately, and they would have gone like down before they had a chance to like be whipped around. And by the time they get whipped around, that impact force is long gone, and they're just being carried around that thing. And so they're liar. He's a liar.
From the top of the bridge. When the 5-member team weighing almost 1,000 pounds reach the end of the cable, the tremendous force snaps their lifeline. For the jumpers, the first injuries are whiplash from the cable. The second and more powerful is the impact of the water 200 feet below the bridge.
That one's
Lori is unconscious, her neck broken. Jeff is not breathing. His neck is also broken. Chaos takes over as the jumpers and the boat crew stare at death all around them. The pendulum death swing claimed no lives, and today all of the injuries have...
Gotta point out, he makes a statement that death is all around them, but that nobody dies, and they called it the death swing, but nobody died, right? So I think he's a liar. He's a liar. He's a liar. Okay, so all right. Okay, this is the Russian rope swing. I don't want to do that one first. This one. Okay. Now don't do this. This appears to be around Chernobyl. I'm not sure, but it appears to be some abandoned buildings in Russia. And well, let's see what they do. Don't do these things.
Ледятку в руку. Вот, держи. Можешь выйти. Все. Готово к полету. Давайте я отпущу. Мы в тебя верим. Ноги прямо. 2, 3.
Would you do that? No, I wouldn't do it. I mean, come on, right? They're on an abandoned building. They're like, sure, I'll do it. The sled off the edge, and yeah, sure, it's fine. Then a rope strung between it, it's gonna be fine. It's gonna be fine. And then that leads to, then let me go. Then this one, same group of people, I'm assuming. Now this one looks painful, to be honest. This one, I think there is a little bit too much slack in the rope. You'll see. Yeah, throw me off there. Yeah, do it. See what I'm saying? There's a little bit too much slack in that rope, I think. Alright. Isn't that crazy? Isn't that crazy? Don't do it. Now you know how to calculate that stuff, okay? Right? I'm sure they did calculations like this beforehand, right? I'm sure they sat down and did this. Okay, so that's normal tangent coordinate system, right? So then this one really quick, we'll set this one up, and like I said, the example problems I'll do in a recorded video that I'll post this afternoon, and we'll go that route. But I have 10 minutes to kind of set this thing up right now. So in this case, remember the coordinate system in here, it's different than normal tangent, right? We have coordinates that start at some origin point, and they go up to the point that we're talking about, and the coordinates, you're going to have one that's in the direction of that vector that's pointed at it. That's going to be the ER direction, right? And then there's going to be one pointed in the E theta direction. Oop, I want to make it perpendicular. All right, so this is going to be the E theta direction. All right, that's that coordinate. It's different than normal and tangent. This one looks, they're pretty close to lining up, except for, yeah, they're pretty close to lining up in this particular curve. But they are different coordinate systems, okay? And in that, this is what the velocity looked like. Right? There's a component in the E theta direction, and there's a component in the ER direction. So the change in this radius, the way this R is changing in the ER direction, and then R omega is going to be the velocity in that direction, okay, in the E theta direction, right? The accelerations, remember that blew up on us, right? And then, in fact, we're going to use cylindrical coordinates for a couple of these problems, right? So there's going to be a Z component. You can also add a Z component to normal tangent as well, if you wanted to. It would still make a cylinder for circles as well. But this is it, right? It's just now our acceleration, when we write down mass times acceleration, we use this for the acceleration in the radial direction, and we use this for the acceleration in the E theta direction. So there's a bunch of variables that are floating around when we do it, okay? And so, like I said, you just write down some of the forces in the R direction is mass times acceleration in the R direction. The acceleration in the R direction has all these components in it. It has an R double dot and an R omega squared. Sometimes these terms go to zero, right? But in its purest form, the forces in the R direction will be equal to this. And so you just do a free body diagram, and then you set it equal to this MR double dot minus R omega squared, and you write it out in each of the directions, and somehow they're all going to be related to each other via kinematics or whatever, and you solve that system of equations, right? You look in the theta direction. You say some of the forces in the theta direction is mass times acceleration in the theta direction. In this coordinate system, you put in the full acceleration in the theta direction, which is R times alpha plus 2R dot omega. You have the Coriolis and you have the tangential acceleration. And then in the Z direction, that one's kind of just treated just like Cartesian. It's just going to be that guy right there. Some of the forces in the Z is mass times acceleration in the Z, which is M times Z double dot, how Z is changing with respect to time, the second derivative of it with respect to time. That's the setup for it, okay? Oh, look, we got 5 minutes. Let's at least set this one up. Just so you kind of see there's some interesting things that are happening here. One of the things here, a lot of these problems have to do with this. So this is a 3D problem, right? This isn't just a 2D problem. This collar right here, right, can slide up and down this rod, right? And then you can picture that, and that rod's gonna rotate about its axis here. So this thing's gonna travel around in a circle, right? It's gonna go around in a circle. And you can imagine if this thing goes really fast, then this collar's gonna move up. If it goes too slow, it's gonna slide down, right? And so we're trying to find the omega right at the cusp of it, minimum constant angular velocity so that the collar does not slip down. So how slow can it go to keep it from going down? You could also imagine how fast it could go to keep it from sliding up, right? Those are kind of two different problems there. But we're trying to find how slow it can go without it falling down, okay? So that's that. First thing, kind of got, we can do a free body diagram, but usually in these problems I like to lay out kind of the arc, just to get a feel for what's happening here. So this, I just mentioned that this collar right here is going to be traveling around in a circle, right? You imagine if this thing's rotating around with an omega, this thing's traveling in a circle. And so I always like to look at this thing from above, right? The path from above, it's helpful sometimes, right? So it's going to be traveling around in a circle. That's not going to be, oh, it is a circle. Right? And our particle is going to be on that circle someplace. I'll draw it right here, right? And then I put my coordinate system on this. This is helpful here. We're doing this in polar coordinates. So my ER is going to be going this way, right? And then my E theta is going to be going this way, right? And my radius here, right? And so that just make this clear. This is from above. I was going to do this intermediate one just so I know what the heck is happening. So if you're looking at this collar from above, that's that black dot. Then we see our coordinates. If we go right to our free body diagram, you don't see all the coordinates because one of them is going to be going into the board. Okay. And then the other thing is important, and we'll call out this radius too. Right, this R is going to be equal to, right, it's not this, they give us this is 0.25 meters, but that's that distance. We need this distance, right? This leg of it there, right, from the center over to it, I guess, that one. And so that's going to be 0.25 times 4/5. Right, it's a 3, 4, 5 triangle, so it's this component of it. The 5 is the 0.25, and so we want this component there, the 4 there. And so 4/5 is the cosine of that angle right there, and so that's 0.2. So that's the setup of it. Okay, well, we got 2 minutes. Let's do a quick free body diagram of it. We'll go right up. We're going to maximize the time. We got isolated object. What are some forces acting on this? That's it. That's what I'm looking for, man. Right, mass times gravity going down. What else? There is friction, right? It says that there's friction in this case, so it's not a smooth rod. So there's friction. Frictions can either go down or up. We're trying to find the minimum so it doesn't slide down. So in that case, if it's not going to be sliding down, then friction's going to be acting opposite. So friction's going to be acting this direction. You can imagine if you're trying to find the other one, if you're trying to find the case where it won't slide up, then friction would be acting the opposite direction, right? It'll be acting down and to the right. But in this case, it's going to be acting up and to the, down to the left. It's going to be, this one's acting up and to the right. That's going to be the mu static times the normal force, right? And then we have the normal force. Okay, let me just put down the coordinates really quick, right? This is where it gets a little bit tricky, right? I'm drawing it, this is it from above, right? So my ER direction is going to be this way. Right. This is it from above. Up here's it from above. This down here is it from the side. So if you're looking at it this way, right? And so ER is going to be going that way. Where's E theta at? It's in the board, right? E theta is in the board, right? And we're looking at it this way, so E theta is in the board. So then what's this direction? That's Z. Or K, I guess what we call that. Okay, we'll leave it there. You guys have an exam. Yeah. All right. Good luck. Good luck at your exam.